Okay, let's dive in. Imagine you're involved in building, modifying, or even just overseeing a rail system. Could be anything, right? A huge new high-speed project, or maybe integrating some new tech into an existing light rail fleet. What's the absolute single most critical thing? Maybe a document, a process, or even just a way of thinking that you need to protect everyone involved.
That's a really central question, isn't it? And it goes right to the heart of why rail is, well, unique. The complexity is huge, and unlike a lot of other infrastructure, the potential consequences of getting it wrong are just catastrophic. You've got immense kinetic energy, fixed infrastructure, people's lives, all interacting at speed. Yeah, the stakes are high.
Right. And the sort of anchor point for managing all that risk, the playbook we're really focusing on today is system safety assurance, or SSA. Now, I know, especially if you're maybe an engineering student or just starting out in project management, assurance can sometimes sound a bit bureaucratic, maybe like just paperwork.
Yeah, I hear that sometimes. But in the real world, honestly, it couldn't be further from the truth. It's absolutely foundational. It's strategic. It's the framework that makes sure, step by step, that whenever we introduce change into the system, any change, we're not accidentally introducing unacceptable hazards along with it.
So it's more than just compliance.
Oh, much more. Think of SSA as the practical tool, the mechanism you use to demonstrate that your organization has actually fulfilled its fundamental duty of care. That's the legal term, and it's non-negotiable.
And how do you demonstrate that?
Well, it's done by actively working to eliminate risks, or at least minimize them, based on this core principle that you have to control hazards so far as is reasonably practicable. You'll hear the acronym constantly.
SFARP.
That's it, ARP, right? Got it. So our mission for this deep dive then is to really pin down exactly who needs to understand and use SSA across all the different bits of the rail sector, and maybe more importantly, why. Why is getting this right the absolute cornerstone of operating well, staying legally compliant, and frankly, staying in business long term? Precisely. And while a lot of the really formalized thinking around this, like the standards we might implicitly touch on, has been heavily developed in places like Australia, the core principles of system safety. They're universal. They apply to any complex system where safety is paramount anywhere in the world.
Okay, so universal principles. Where do we start? If we want to really understand SSA, where's the ground floor?
The ground floor isn't actually technical, it's legal. You have to start with the law. Yeah. SSA isn't driven by, best practice preference or someone thinking it's a good idea. It's driven by a legal mandate. The whole framework, everything we'll talk about, it's rooted in this concept of duty of care.
Okay, duty of care. Where does that come from?
It's established in broad national safety laws, think
Mhm.
Work Health and Safety Acts or their equivalents, and then reinforced by specific railway legislation, like the Rail Safety National Law in Australia, but every jurisdiction has something similar. These laws don't just suggest safety, they demand due diligence from organizations operating railways.
Okay, so it's a demand, a legal obligation. It's not just about trying not to get fined then, it's something more continuous.
Exactly. It's a continuous, legally defined obligation to be proactive about safety. You can't just react to accidents. You have to anticipate and manage risks before they cause harm.
And what does that proactive effort actually look like when an engineer is making a decision on a project? How does duty of care translate into, say, choosing one design over another?
It translates directly through that SFAR principle we mentioned,
Okay.
so far as is reasonably practicable.
Right.
This definition is key. It mandates that you must eliminate or minimize all reasonably foreseeable safety hazards, up to that standard of reasonably practicable.
Okay, reasonably practicable. That sounds, well, reasonable. But what does it mean in practice? Does it mean you have to spend absolutely any amount of money to make something infinitesimally safer?
No, and that's a critical distinction. Practicable forces you into a process of robust due diligence and risk assessment. You have to weigh several things. First, what's the likelihood of the hazard actually occurring? Second, what's the potential degree of harm if it does occur? And third, this is the practicable part. What do we actually know about controlling this hazard? What technologies or methods, the means, are available? And what are the costs, both financial and in terms of difficulty or time of implementing those controls?
Okay, let's try and make that concrete. Say we're building a new section of railway line, and it needs to cross a road in a reasonably busy area, a level crossing. We know that's inherently a hazard, right?
Absolutely. The hazard is the potential conflict between trains and road vehicles or pedestrians. So applying SFARP, we have to look at controls.
A basic control might be flashing lights, warning bells, maybe boom gates that come down.
Yes, that's a common control set. But then the SFRP question kicks in. Is it reasonably practicable to do better? Can we improve upon that? Well, technically, yes. We could eliminate the hazard almost entirely by building a grade separation, putting the road over the railway or the railway over the road with a bridge or an underpass.
Right, that gets rid of the conflict point completely, much safer.
Technically superior, definitely safer. It essentially eliminates that specific hazard. However, building that grade separation might cost, say, $100 million, involve acquiring lots of land, disrupting the community for years during construction.
Okay, so the costs and difficulty are huge compared to the level crossing setup.
Exactly. And this is where practicability comes in. SFRP doesn't automatically demand the absolute best possible technical solution if the cost or difficulty of achieving it is grossly disproportionate to the safety benefit gained compared to other effective controls.
So if the enhanced level crossing, maybe with really good sensors, reliable boom gates, clear sight lines, maybe even some predictive warning systems, reduces the risk to a level that's already considered acceptable elsewhere in the network for similar traffic levels.
And if the cost of that full grade separation is truly massive and disproportionate to the remaining, now much smaller risk, then the enhanced level crossing might be deemed SFIRP in that specific context.
And this is a big but. I guess if that same crossing was, I don't know, on a high-speed line with trains going through every 10 minutes and carrying thousands of passengers plus thousands of cars using the road.
Then the potential consequence part of the SFIRP equation skyrockets. The degree of harm is much higher. And the reasonableness of spending that $100 million on grade separation starts to look very different. The practicability threshold shifts, and that overpass might become effectively mandatory to meet the SFA requirement.
Okay, that makes sense. It's not a fixed line. It depends heavily on the context, the risk, the consequences, and what's realistically achievable.
Precisely. And the whole point of SSA, the process, is to provide the documented evidence, the justification that shows you systematically went through that SFAP assessment. You need to demonstrate the rigor you applied to justify the controls you eventually chose, proving they were the highest standard reasonably achievable under those specific circumstances. And you need objective evidence to back all that up.
Evidence is key then.
Absolutely. Which leads us to another really crucial point, especially for people in leadership roles. That legal duty of care we talked about, it's non-transferable. Completely.
What do you mean non-transferable? Surely if you hire a big expert consultancy to design something...
You can hire them, yes. You can contract out the design. You can contract out the construction. You can contract out the maintenance. But the ultimate legal responsibility, the duty of care for the safety of the overall system, always remains with the accredited organization, usually the main rail operator or the infrastructure owner.
So let's say an operator hires contractor X to design a new signaling system. Contractor X messes up, there's a flaw in the design, and years later it contributes to an incident. The operator can't just say, well, contractor X designed it, it's their fault.
Nope. They absolutely cannot. The operator holds the overarching duty for everyone who might interact with their railway assets. Their own employees, the passengers, the contractors working on the line, even the general public crossing a bridge over the tracks.
No.
If you, as that accredited operator, failed to ensure the contractor X's design process met the SFA-RP standard, if you didn't apply your own SSA processes rigorously to oversee and assure their work, review their safety case, check their evidence, then you have failed to discharge your legal duty.
So the consequences fall back on the operator.
Squarely, both legally and reputationally. That constant underlying liability is what fundamentally transforms SSA from just, a compliance checkbox exercise into a core strategic management practice. It's about survival.
That's fascinating because it reframes safety completely. When it's managed strategically like that, it stops being just a cost center on the balance sheet. It actually becomes an investment that directly mitigates potentially enormous financial liabilities, protects the confidence of investors or government funders, and reduces the risk of those catastrophic operational meltdowns that can damage a company's reputation for decades.
You've hit the nail on the head. It defines the long-term health and viability of the business.
So it proves that safety isn't like a separate department you can silo away. It has to be woven into the absolute core operating philosophy of the organization, essential for both commercial success and just meeting the basic legal requirements to operate at all.
That's it, exactly. It's fundamental.
Okay, so we've established the why, the legal mandate, the non-transferable duty of care, the strategic importance. Now let's dig into the who. Who are the actual people from the boardroom down to the worksite who need to understand and execute these SSA principles?
Right. And before we break down the roles, it's crucial to remember what you said earlier. SSA applies universally across the rail industry.
Yeah, not just the big mainline networks.
No, absolutely not.
Yeah.
Whether you're running a tiny 2-kilometer heritage railway with volunteer staff and maybe one steam engine, or you're managing a vast metropolitan network with hundreds of trains and complex signaling, the fundamental principles apply. If you're operating a system where failures can lead to harm, you have a duty of care, and SSA is the way you demonstrate you're meeting it.
The scale and complexity will be different, obvious.
Hugely different. The specific hazards might vary, maybe low-speed collision risks versus complex software failure modes, but the mandatory process of identifying hazards, assessing risks, implementing controls, and documenting it all to that SFRP standard, that remains constant. It just needs to be scaled appropriately.
Okay, so scaled but universal. Let's break down the key groups of people involved. You mentioned maybe 4 categories.
Yeah, we can think of it in roughly 4 main groups. Let's start right at the top.
Okay, category 1, the leaders and visionaries. So we're talking executives, board members, senior managers.
Exactly. Their role isn't necessarily in the technical detail, but it's absolutely critical for governance. They must understand the high-level SSA management requirements. They need to grasp the weight of that organizational duty of care we just talked about.
So the CEO doesn't need to know how to perform a fault tree analysis, maybe.
Probably not the specifics, no. But they absolutely need to understand why it's being done, what level of risk the organization is accepting, and what the implications are if the SSA process flags a major issue. They're the ones who ultimately approve the budgets for safety-critical systems, sign off on the resources for safety training, fund independent assessments.
Their decisions set the whole tone, don't they? The safety culture.
Completely. If the leadership signals, even subtly, that they see SSA as just red tape slowing down project delivery, that message cascades down instantly. The project manager feels the pressure. They lean on the engineers, and suddenly corners might start getting cut, or risks might be rationalized away. Effective SSA requires visible, genuine commitment right from the very top. They need to champion it.
Makes perfect sense. Okay, who's next?
Next up, category 2. The practitioners and implementers. This is really the core group, probably many of the people listening. We're talking about the designers, the engineers, systems, electrical, mechanical, civil, all of them, the dedicated safety managers, and the assurance managers.
These are the people actually doing the technical work of SSA.
Yes, they are the technical engine. They take that high-level legal mandate and the SFARP principle and translate it into demonstrable practical safety measures within projects and operations. They're the ones running the hazard identification workshops, writing the detailed safety requirements that go into specifications, analyzing failure modes, ensuring design decisions, actively consider safety from the start.
So for this group, SSA isn't just a concept, it's their day-to-day toolkit.
It's their framework. It's the structure that allows them, frankly, to defend a safe, robust design against inevitable pressures, schedule pressure, cost pressure. They are the primary guardians of the SFAR principle at the technical level, ensuring the engineering is sound and the risks are properly controlled. They generate the evidence.
They're providing the technical justification that lets Category 1, the leaders, sleep at night, essentially.
You could put it that way, yes.
Okay, who's in Category 3?
Category 3, the deliverers. This is a really broad group. It includes project managers, construction contractors, equipment suppliers, maintenance providers, even procurement authorities who are buying new assets or services.
So pretty much anyone involved in making changes happen on the ground, whether it's building something new, supplying a part, or managing the overall project.
Exactly. Their scope is huge. Their responsibility is to ensure that whatever specific contribution they're making, whether it's pouring concrete for a bridge pier, supplying a new batch of brake pads, writing software for a control system, or managing the project schedule, adheres to the overall SSA requirements set by the main client organization, the Category 1 and 2 folks.
So if you're a company supplying, say, new train wheels, you can't just deliver the wheels.
No way.
Yeah.
You have to provide the wheels plus the assurance evidence. That means documentation, proving the design meets safety standards, the manufacturing process was controlled, maybe fatigue life calculations, quality checks, even clear maintenance instructions, all showing that your wheels integrate safely into the bigger rail system and meet the client's safety targets. Every significant contract needs to have a clear, robust SSA linkage.
And for project managers specifically, their role seems crucial here in balancing everything.
Absolutely critical. The PM has to weave the SSA activities,
Yeah.
the hazard reviews, the V&V periods, maybe procuring an independent safety assessor into the main project schedule and budget. They have to ensure these safety milestones are treated with the same seriousness and rigor as, say, pouring the foundations or laying the track. Safety can't be an afterthought. It has to be planned and resourced from day one.
Okay, that covers the people making it happen. What's the last category?
The final group, Category 4. The overseers. These are the external regulatory bodies. Think of the National Rail Safety Regulator in Australia or similar bodies worldwide.
Their job is to check up on everyone else.
Essentially, yes.
Yeah.
They review the operator's overall safety management system, they audit compliance on specific projects, they grant the necessary accreditations and licenses that allow the railway to operate legally. And what are they looking for when they do these reviews?
The SSA documentation?
Precisely. SSA is the language the regulators speak. The safety cases, the hazard logs, the V&V reports, the ISA findings, this is the objective, traceable, auditable evidence they need to see. It's how they verify that the operator, Category 1, has systematically and thoroughly discharged their duty of care, using the processes managed by Category 2 and delivered by Category 3.
So without a solid SSA system producing that credible evidence, the regulators just won't sign off.
They won't. They can't. It's the final gateway to getting operational approval or maintaining it. It's that important. So we've covered the why and the who. The next logical question is when. When do all these people actually need to apply SSA principles?
Right. Is it just for brand new projects?
That's a common misconception, but no, definitely not. The fundamental rule is straightforward, but it has really far-reaching implications. SSA is required whenever changes are introduced that may affect safety.
Okay, the key word there is change. That sounds potentially very broad.
It is broad, intentionally so. Obviously includes the big things. Constructing a new line, delivering a major resignaling project, buying a whole new fleet of trains. Those are clear triggers. That's more than that. Oh yes, it also covers seemingly smaller things. Updating the software on a signaling control system. That's a change SSA applies. Modifying the way passengers flow through a station platform. Change. Potential safety impact, SSA applies. Changing the scheduled frequency for inspecting track welds. Change. Potential safety impact, SSA applies. Even introducing a new type of diagnostic tool for maintenance crews could trigger it if using the tool incorrectly might affect safety. Wow, okay. So basically, if you alter the established baseline of how things are designed, built, operated, or maintained, and that alteration could foreseeably impact safety, even indirectly, then the SSA process needs to kick in.
You've got it. Any deviation from the verified safe baseline requires assurance. That must create a real tension for the practitioners, though. The amount of effort involved in doing SSA for, say, a tiny software patch versus building 50 kilometers of new track must be vastly different. How do you handle that scaling?
That's absolutely critical in practice. You must tailor and scale the SSA effort based on the specific change. You need to consider the complexity of the change, its potential impact, how widely it affects the system, and the inherent risk level associated with that part of the system.
So it's proportional.
Exactly. Proportionality is key. A minor procedural change might only require a quick hazard review meeting, maybe updating a single document and issuing a brief safety notice. It's still SSA, but it's scaled right down. Building that new 50-kilometer freight line, however, that demands a full-blown System Safety Assurance Management Plan, the SMMP, which could run to hundreds, even thousands of pages, detailing hazard analyses across civil, mechanical, electrical, operational domains, requiring extensive V&V, likely an ISE. The rigor of the thinking process, hazard or risk control of evidence, is the same, but the depth and breadth of the documentation and analysis is scaled dramatically.
Okay, that makes sense. It avoids bureaucracy for tiny changes, but ensures full rigor for major ones. This idea of applying SSA to changes throughout the system's life brings us to the whole of life concept, doesn't it? SSA isn't just something you do at the start and then forget about.
Absolutely not. It's a living process. It has to span the entire life cycle of the asset or system. We can generally think about its application across three main phases.
Okay, what's the first phase?
First is design, delivery, and commissioning. This is the upfront phase, creating something new or significantly modifying something. This is where the foundational risks have to be identified and designed out or controlled right from the start.
So getting in early is key.
It's paramount. SSA requires that safety thinking starts at the earliest concept stage, even before detailed design begins. You need to identify major hazards and define high-level safety requirements then. Trying to bolt safety on after a design is largely complete is probably the single biggest cause of project delays, cost blowouts, and frankly, residual safety risks.
Can you give an example?
Sure. If you're designing a new type of passenger train, very early on, during the concept phase, SSA principles demand you think about: what are the credible collision scenarios? What level of crashworthiness does the structure need? What are the fire risks, and what performance level do fire detection and suppression systems need? How will passengers evacuate safely? What braking performance is required under various failure conditions? These safety requirements, derived from early hazard analysis, must be defined before engineers start finalizing the detailed vehicle architecture, the materials, the software logic.
So SSA effectively provides the safety inputs into the requirement specification, making sure that every major engineering decision down the line can be traced back to controlling a specific identified hazard.
Precisely. It sets the safety baseline for the project. Then, once the system is built, tested, commissioned, and starts running, we move into the second phase: operation and maintenance.
So the assurance work doesn't stop once the ribbon is cut.
Not at all. The focus shifts, but the need for assurance continues. You need ongoing assurance activities to confirm that the systems continue to meet their original safety objectives out there in the real, messy operational world.
How do you do that? What feeds into that ongoing assurance?
Real-world data is crucial. You use operational information reports from drivers about near misses, data loggers showing equipment performance, statistics on component failures, feedback from maintenance staff, records of track condition measurements. All this data gets fed back into the assurance process.
So you're constantly checking, are the assumptions we made during the design phase still valid? Are the controls we put in place 5, 10, 20 years ago still effective, given maybe the fleet is older now, or traffic density has increased, or the environment has changed?
Exactly. It's a reality check. And this is where you see a really strong link between safety assurance and RAM's reliability, availability, maintainability, and safety. They work hand in glove. Well, say your RAM's analysis shows that a particular type of axle bearing is starting to fail more frequently than predicted in the original design life calculations. That's not just a reliability problem impacting train availability. It immediately becomes a safety assurance issue, because that bearing failure could potentially lead to a derailment. So the RAM's data triggers an SSA review. Is the risk still SFSO? Do we need to change the inspection frequency? Do we need a redesigned bearing? Do we need operational restrictions until it's fixed?
Got it. So operational data continuously validates or challenges the safety case. What's the third life cycle phase?
The third phase is modification and disposal. SSA even applies right at the end of a system's life or when it's being significantly changed out.
Even when you're getting rid of something.
Yes. Think about decommissioning an old signaling system to replace it with a new one. The SSA process needs to assure the safe transition. How do you ensure the old system is fully deactivated and electrically or physically isolated so it can't interfere with the new one? How do you manage the cutover period safely? What happens if the new system fails during commissioning? Can you safely revert? Even the physical demolition and removal of old assets, like taking down an old bridge, needs safety assurance to protect workers and ensure debris doesn't create hazards for adjacent operational lines.
Right, so ensuring no residual hazards are left behind, either physically or functionally.
Correct. This whole life cycle perspective highlights that SSA is fundamentally about managing change safely, and it creates this inherent need for a continuous improvement loop.
It's not static.
It's never static, because the railway itself isn't static. If a train manufacturer releases a critical software patch for the braking system, that patch is a change. It triggers a mini SSA cycle. What's the impact of this patch? Does it introduce any new failure modes? How do we verify and validate it doesn't negatively affect existing safety functions? How do we roll it out safely across the fleet?
So it's constantly iterative.
It has to be, because risk itself is dynamic.
Yeah.
The assumptions you made, the controls you designed at the start, they need to be constantly reviewed and refined as the project progresses, as new operational data comes in, as component suppliers change, or as the regulatory landscape inevitably shifts over time. It's a mandatory feedback loop, constantly working to revalidate that the system is still meeting that SFIRP minimum standard throughout its entire life.
Okay, this is great. We understand the why, the who, the when. Now let's really get into the weeds, technically speaking. This feels like the crucial bit for the engineers listening, category 2, the practitioners. If you're tasked with doing SSA on a project, how do you actually execute it? What's the mechanism?
All right, let's unpack the typical process. It almost always starts with creating a master plan for how safety will be managed on that specific project or change. This is usually called the System Safety Assurance Management Plan, or SSMP.
The SMMP. Okay, what does that do?
Think of it as the constitution or the charter for safety for that particular piece of work. It formally defines things like what is the exact scope of the system or change we're assuring? What specific safety standards, national, international, company standards, will we be applying? What specific SSA processes and methods will we use? And critically, who is responsible for doing what? Who generates the hazard logs? Who reviews the risk assessments? Who approves the safety case evidence? It sets out the entire framework up front.
So everyone knows the rules of the game before you start playing.
Exactly. It ensures consistency and clarity. Once that SMP is agreed upon and formally issued, the structured process really kicks off. The first major technical step is usually an impact assessment.
Impact assessment. What's that assessing?
It's assessing the potential safety impact of the proposed change on the existing railway system. You can't manage the risks if you haven't clearly defined how your change interacts with everything else. It identifies which parts of the current system tracks, signals, power, operations, maintenance interface with your change. It establishes the baseline safety requirements that already exist in those areas. And this assessment helps determine the necessary rigor for the subsequent SSA activities.
So it helps with that scaling we talked about.
Precisely. If the impact assessment shows your change is minor and isolated, maybe the follow-on safety case documentation can be quite concise. But if it shows your change impacts, say, the core train control system on a busy high-speed line, then the assessment flags that maximum rigor, complexity, and evidence gathering will be required.
Okay, impact assessed. What's next? This must be where the hazard stuff comes in properly.
Yes. Now we move into the real heartland of engineering safety. Hazard identification and management. This is where it gets systematic. Identifying potential hazards, assessing the risks they pose, and defining how we're going to mitigate or control those risks down to that SFIRP level.
And this is where engineers use those specialized acronym-heavy methods, right? PHI, PHA. Can you walk us through the main ones, maybe in the order you typically use them?
Sure. These methods tend to be progressive, becoming more detailed as the project design matures. You often start very early, maybe even at the feasibility or concept stage, with a preliminary hazard identification, PHI.
PHI, what's that involve?
It's often a structured brainstorming session with experienced engineers from different disciplines. The goal is simply to list every conceivable hazard associated with the project concept, no matter how unlikely it might seem at this stage. Think broad categories: collision, derailment, fire, electric shock, human error, environmental factors. You're just trying to get everything out on the table before any detailed design choices lock you in. The output of the PHI helps shape the initial high-level safety requirements.
Okay, so a broad sweep first.
Yeah.
Then what?
Next, as the concept firms up a bit, you typically conduct a preliminary hazard analysis, PHA. The PHA takes the big list of hazards from the PHI and starts to do a first-pass assessment of their potential likelihood and consequence. You're trying to rank them, figure out which ones are the most significant risks that need tackling early. The PHA helps determine if the inherent risk is broadly acceptable or if specific mandatory safety controls need to be baked into the design requirements right from the outset.
So the PHA tells you what you really need to worry about controlling before you get deep into the detailed design work.
Essentially, yes. It prioritizes the risks. Then, as the design matures and you have actual system architectures and subsystem designs emerging, you move to more detailed analyses. A key one is the System Hazard Analysis, SHA.
SHA. How's that different?
The SHA is much more focused on the interfaces between different parts of the system. How do subsystems interact? And critically, how might failures propagate from one part to another? For example, an SHA might look specifically at the interface between the signaling system and the track circuits that detect trains. What happens if a track circuit gives a false clear signal? How does the signaling logic respond? What are the potential failure modes and resulting hazards from that specific interaction? It gets quite detailed.
Okay, so SHA looks at system-level interactions. What about when you get right down to individual components or bits of software?
That's where you deploy even more granular tools. Things like failure modes and effects analysis, FMEA, or its cousin failure modes, effects, and criticality analysis, FMEA, are very common for hardware and software components.
FMEA Mecca, what do they do?
An FMEA systematically examines every potential failure mode of a single component, like, say, a power supply failing, a sensor getting stuck, a valve not opening, a line of code having a bug, and then analyzes the effect of that specific failure on the immediate subsystem, and then potentially on the overall system safety. You trace the consequences upwards.
And you mentioned fault tree analysis, too. FTA.
Right, fault tree analysis, FTA, is another powerful tool, often used for complex systems. It works the other way around from FMEA. You start with an undesirable top-level event, like train passes signal at danger, and then you logically work downwards to identify all the possible combinations of lower-level failures, component failures, human errors, software faults, that could lead to that top event occurring. It's great for understanding complex causal chains. You might also hear terms like FFA, failure flow analysis, which are variations on these themes.
Wow, okay. So there's a whole suite of analytical tools the practitioners use to really dissect the system, identify the hazards lurking within it, figure out the controls needed, and then formally define those controls as safety requirements that have to go into the design specifications and procedures.
That's the core loop, yes. Identify hazard, assess risk, define control, specify requirement.
So once you've done all that analysis, set the requirements, and the engineers have actually designed and built the controls, whether it's a new piece of software, a stronger train axle, a specific maintenance procedure, you hit what sounds like a really crucial stage, verification and validation, V&V. You mentioned this is about objective evidence, and I suspect this is where many early career people might stumble. What does that actually mean in practice?
Yeah, V&V is absolutely fundamental. It's the show me the proof stage. And it's important to distinguish the two terms. Verification asks, did we build the system correctly? Does it meet the technical specifications and requirements that we wrote down based on our hazard analysis? Validation asks, did we build the right system? Does it actually meet the user's operational needs safely? And critically, are the safety controls we designed effective in the real world at minimizing the risks we identified?
Okay, verification is built correctly, validation is built the right thing effectively. What does the objective evidence look like then? If I'm the V&B manager, what am I collecting or producing?
You're collecting tangible, documented proof. It could be a whole range of things depending on what you're assuring. It includes things like detailed test reports from physical trials, showing, for example, that the train's braking distance met the specified requirements under different load and weather conditions. Simulation results demonstrating that the control software behaves correctly when you deliberately inject fault conditions. Inspection certificates and material traceability records proving that critical components were manufactured to the correct standard from the right materials. Formal safety audits confirming that operational or maintenance procedures are being followed correctly by staff out in the field. Analysis. Reports like stress analysis for mechanical parts or timing analysis for software showing the design margins are adequate. Certificates of conformity for body and equipment.
So it's concrete stuff, not just saying we think it's safe.
Absolutely not. Every claim made in the safety argument, every assertion that a risk is controlled must be backed up by this kind of verifiable, objective evidence. Without that traceable evidence trail, the safety case is just unsupported opinion, and it collapses under scrutiny.
Okay. Now, because project teams, they're invested in their own designs, they want them to succeed, there's always a risk, even subconsciously, of bias creeping in, maybe overlooking something.
That's a very real human factor.
So the next step you mentioned provides a check against that, the Independent Safety Assessment, ISA.
Exactly. For most significant rail projects, particularly those involving major changes or novel technology, an ISA is mandatory. This involves bringing in a completely separate external organization, often a specialist consultancy, that might even be accredited by the regulator itself to review the entire SSA process, followed by the project team.
So the ISA doesn't directly certify the system is safe.
No, that's a common misunderstanding. The ISA certifies that your process for determining and demonstrating safety was rigorous, that it complied with the relevant standards, like the SMMP, that the evidence supports the claims, and that the assessment appears free from undue internal pressure or bias. They act as an independent auditor of your safety assurance work.
What do they look at?
They'll audit everything. The hazard logs, the risk assessments, the FMEAs, the V&V test plans and reports, the traceability between hazards, controls, requirements, and evidence, and ultimately the overall safety case documentation that pulls it all together.
And what happens if they find problems?
An ISA report will typically raise findings or observations. These might point out gaps in the hazard analysis, weaknesses in the V&V evidence for a particular control, inconsistencies in documentation, or maybe instances where the justification for accepting a residual risk wasn't robust enough. These findings usually have to be formally addressed and closed out by the project team, often requiring more analysis or testing before the ISC will give their final positive assessment.
So that external scrutiny adds a crucial layer of integrity. especially when, inevitably, project schedules get tight and there might be pressure to cut corners.
It's absolutely essential for maintaining rigor and objectivity. Then, assuming the ISA is satisfied and all the V&V evidence is complete and accepted, we move to the final steps: configuration and acceptance.
Configuration and acceptance, what does that involve?
This is where the as-built and as-tested design, along with its supporting safety case, is formally accepted by the organization. Category 1. This acceptance is usually managed through strict procedural controls, often involving something called a Configuration Control Board, CCB, or a similar change management authority.
A configuration control board, what's their job?
They are the gatekeepers for the approved baseline. Once a system configuration is formally accepted with its safety case, the CCB manages all subsequent changes to that baseline. Their role is to ensure that the physical system operating out on the tracks today, or the software running in the control center, exactly matches the configuration that was proven to be safe and formally accepted.
So if someone wants to make even a small change later on, tweak a software parameter, use a different type of bolt in maintenance.
That proposed change must go through the formal configuration control process. It gets assessed for its potential impact, including safety impact. It might trigger a mini SSA cycle, require updated V&V, and needs formal approval from the CCB before it can be implemented. This maintains the integrity of the safety case over the system's life and provides that crucial legal traceability. You always know exactly what configuration is running and that its safety has been assured.
That sounds like a lot of process, but essential for keeping track.
It is essential. And underpinning this entire mechanism, from the SMP right through to configuration control, are two fundamental enablers: competence and governance.
Competence and governance, tell me more.
Well, quite simply, the quality and validity of the entire SSA effort depend entirely on the skills, qualifications, and experience of the people doing the work, particularly those Category 2 practitioners. You need competent engineers, competent safety analysts, competent V&V managers. Organizations have a duty to ensure their staff are competent for the safety roles they perform.
And governance.
Governance refers to the organizational structures and processes that ensure safety has the right level of authority and visibility. It means ensuring that the safety specialists, the assurance managers, have a clear reporting line, often directly to senior management, Category 1, and that they have the authority to influence critical project decisions or even stop a process if they identify an unacceptable risk. Safety can't be overruled by commercial or schedule pressure without a very formal, high-level acceptance of any residual risk. Good governance ensures safety has a strong voice at the decision-making table.
Okay, we've really gone deep into the how there, the nuts and bolts of the SSA process. Let's maybe zoom back out a bit and circle back to the strategic why. We touched on it earlier, but SSA isn't just about ticking legal boxes or managing safety risks in isolation. It delivers broader business value, doesn't it?
Absolutely. When done well, its value goes far beyond just preventing accidents, although that's obviously paramount. It provides that proactive, evidence-based confidence. Confidence for the organization itself, for its leaders, for its investors, for the regulator, and for the public, that the inherent hazards in running a railway are understood and are being effectively controlled down to that SSAP level.
It's about being able to say, we know the risks, we've systematically addressed them, and here's the proof.
That's it, exactly.
Yeah.
And that documented confidence underpins so much else in the business.
Now, a key point here, I think, is that SSA doesn't or shouldn't operate in its own little bubble. For it to be truly effective and deliver that value, it needs to be deeply integrated with pretty much all the other key engineering and management disciplines on a project, right?
Oh, completely. It cannot be a silo. If it is, it fails. Effective SSA requires constant coordination and information sharing. Think of it maybe like a complex piece of machinery itself. All the parts have to work together smoothly.
Or maybe like a symphony orchestra.
That's a great analogy.
Yeah.
SSA is perhaps the conductor, ensuring the overall safety performance meets the required standard. But all the different sections of the orchestra, the other assurance disciplines, need to be playing their part harmoniously, reading from the same score, as it were.
Okay, so who are the main sections in this assurance orchestra that SSA needs to coordinate with?
Well, first and foremost, you need strong systems engineering. SE provides the overall structure, defines the system architecture, manages the interfaces between components, and importantly, manages the requirements lifecycle. SSA relied heavily on the framework and discipline that good systems engineering provides.
Okay, systems engineering is fundamental. What else?
Then you absolutely need RAM's reliability, availability, maintainability, and safety. We touched on this. RAM's analysis provides critical inputs to SSA, like predicting component failure rates, identifying reliability weaknesses that could become safety issues, and ensuring maintenance strategies support safety. In turn, SSA outputs the safety requirements often drive RAM's targets, e.g., needing a certain reliability for a safety-critical brake component. They're deeply intertwined.
Right, RAMs and safety work together. Who else is crucial?
Human factors integration is massive. HF experts analyze how people, drivers, controllers, maintainers, passengers interact with the system. They identify potential human error traps in designs or procedures. Their findings are critical inputs to hazard analysis within SSA, ensuring that the system is designed to be resilient to foreseeable human mistakes. You can have the most technically brilliant system, but if the user interface is confusing under pressure, it's not safe.
That makes sense. People are always part of the system. What about newer areas?
Absolutely vital today are disciplines like environmental management, ensuring, for instance, that construction or operations don't create environmental hazards that could loop back and cause safety risks, like unstable embankments. And perhaps the fastest growing area of integration is cybersecurity assurance.
Ah, the cyberlink.
That's it.
That seems incredibly important with modern digital railways.
It's non-negotiable now. So many safety functions rely on software, data networks, remote control. A cyber attack on a signaling system or a train's control network isn't just an IT problem. It's a direct threat to physical safety.
So how do they integrate? Does cybersecurity assurance feed into SSA?
Yes. The cybersecurity team identifies potential vulnerabilities and threats to the digital systems. They propose mitigation controls, things like firewalls, encryption, access controls. But then SSA needs to take those outputs and ensure two things. First, that the cyber risks themselves are assessed for their potential safety consequences. e.g., could a breach cause unintended acceleration or braking? And second, that the cybersecurity controls being implemented don't inadvertently interfere with the system's ability to perform its fundamental safety functions when needed. e.g., can the emergency brake command always get through, even if the network is under attack?
Wow. So the cyber assessment findings become direct inputs into the overall system safety case, needing verification and validation just like any other safety control.
Exactly. The integration has to be seamless. When you get this coordinated, integrated assurance approach working well, the strategic business outcomes become really clear, and they hit the bottom line.
Okay, let's summarize those high-level benefits again. What are the big wins for the business from doing SSA properly?
First, obviously, is proactive risk management. By systematically finding and fixing hazards before they cause accidents, you avoid the potentially astronomical costs associated with major incidents. Legal claims, compensation, fines, equipment damage, reputational ruin. That's a direct financial benefit.
Makes sense. Avoid the catastrophe. What else?
Second is enhanced business continuity. A system that's been rigorously assured through comprehensive V&V and maybe an IDIS is inherently going to be more robust, more reliable. You've designed out weaknesses, you've tested it thoroughly. This leads to fewer unplanned breakdowns, reduced operational disruptions, fewer service delays. That means greater efficiency, better customer satisfaction, and lower operating costs over the system's life.
So safer systems tend to be more reliable systems too.
Generally, yes. The disciplines reinforce each other.
Yeah.
Third, and this is often overlooked but really exciting for engineers, SSA acts as an enabler of innovation.
How so? People sometimes see safety processes as barriers to new ideas.
It can feel that way if done badly, but good SSA is the opposite. It provides the controlled, structured environment that allows you to introduce new technologies or new ways of working safely. Think about driverless trains, or using AI for predictive maintenance, or implementing advanced communication-based train control. You simply cannot deploy these innovations responsibly without a rigorous SSA framework to identify the novel hazards they might introduce, to define the new safety requirements for digital systems, to thoroughly test and validate the controls, and to assure the safe integration with existing infrastructure.
So SSA doesn't block innovation. It actually provides the pathway to implement innovations securely.
Precisely. Without SSA, potentially game-changing modernization gets paralyzed by unmanaged, unknown risks. With SSA, you have a methodology to proceed with confidence.
Okay, that's a powerful point. And the final big benefit.
The final one comes back to confidence, specifically stakeholder confidence. Being able to demonstrate, with hard evidence generated through the SSA process, that your railway is safe and well-managed is absolutely crucial. It builds trust with regulators, making licensing and approval smoother. It builds trust with clients or government funding bodies, helping secure future projects and investment. It builds trust with your employees and ultimately with the traveling public. That documented, evidence-based safety performance underpins the organization's reputation and its social license to operate. #outro. So if we try and wrap this all up, especially for you listening, maybe you're that engineering student or early career professional, the key thing to take away is that System Safety Assurance, SSA, it's really not just some optional document you file away or an administrative task to get through. It's much bigger than that. It's the core strategic management practice that genuinely makes rail organizations safe, keeps them reliable, and ultimately makes them successful businesses over their entire operating lifespan.
Yeah, and for those of you who are heading into those Category 2 roles, the practitioners, the engineers, the designers really getting your head around SSA, understanding its principles and its processes. It's basically non-negotiable for a career in rail. This framework, this way of thinking, it's going to define how you approach managing change, how you demonstrate your professional competence day to day, and how you effectively influence those really critical decisions about safety and investment on pretty much every significant project you'll ever work on in this sector.
It really is the unifying language, the professional framework for managing safety across the entire industry. It provides that essential structure for translating the legal duty of care into tangible, objective, technical reality on the ground.
Which I think leaves us with a really interesting, maybe slightly provocative final thought for you to mull over as you go into your careers. We've talked a lot about SFA for managing safety risks so far as is reasonably practicable, but we also know that major rail projects are constantly under pressure to innovate faster, deliver quicker, be more efficient. So the question for you, as a future engineer or safety professional, is this. How do you ensure that those pressures, the need for speed, the drive for innovation, never subtly lead to a redefinition or a watering down of what practicable actually means? How do you hold the line, ensuring that the fundamental safety baseline we all rely on isn't compromised in the rush to deliver? Finding that rigorous ethical balance, well, that's probably the defining challenge and responsibility of modern railway safety engineering.